Okay, so good morning, everyone. Thank you for joining Unit Operation 1 class today. So we are going to continue our study to the next subchapter, which is about the agitation and mixing. Okay, so we have two terms here, mixing and agitation. So what is the difference between the two? Yeah. So mixing, yeah, it can be defined as a taking of two or more separate phases, let's say solid and fluid or liquid and liquid, yeah, and causing them to randomly distributed through one another. So that's mixing, yeah. And what is agitation? Yeah, so agitation is forcing a fluid by mechanical means to flow a circulatory or other pattern inside the vessel. Okay, so if I can say, mixing is the name of the process, agitation is one of the techniques used to mix two separate phases. Okay, now, several uses of agitation. First is to blend two miscible liquids. Second is to dissolve solid in liquid. Third is to disperse gas in liquid. Fourth is suspend fine solid particles in a liquid. The fifth is to increase the heat transfer between the fluid and a coil or jacket inside in the vessel wall. Now, okay, so we have three course outlines here. First is flow pattern and design of agitation system. Second is agitator scale up and down and mixing miscible liquids. Third is spatial agitation system and mixing of solids, base, and viscous materials. Okay, now, so there are three types of flow direction. Yeah. So by agitation, there are three types of flow direction. First is radial flow. So it is where the fluid flows in a circulatory pattern following the curvature of the vessel wall. Yeah, you can see the video here. You can just click the YouTube link, yeah, to see what the radial flow is. The axial flow, yeah, is where the fluid flows in vertically, yeah, from top to bottom or vice versa from bottom to top. Yeah, so it produces more fluid motion and useful in suspension of solid. Yeah. So if radial flow is parallel to the curvature of the vessel wall, the axial flow, it's where the fluid flows vertically up and down. Yeah, and since it's flows vertically, yeah, it produces more fluid motion, and it is useful for suspending solid inside a liquid. Yeah, you can see this video, yeah, to compare the two, yeah, radial flow and axial flow. Now, and then the third one is tangential flow. Yeah, so tangential flow is actually the combination between the radial flow and axial flow. Okay, yeah, you can take your time to watch this YouTube link. Yeah, you can just pause my video now, watch the two YouTube links here. Yeah, watch the two YouTube videos here, and then find the differences. And then after that, you may continue my class. So that, okay. Now, you can also see, yeah, this YouTube video, yeah, for the difference between the flow patterns. Yeah. Okay. Now we continue. Yeah. Now, for a very vigorous agitation, yeah, usually vortex, yeah, or swirling, yeah, flow patterns will develop. Ya, akan terbentuk pusaran-pusaran, ya, or vortex. Yeah. Now, this vortex is actually undesirable, yeah, since it causes air entrainment and not good for mixing. Yeah, it will reduce the mass transfer. Okay. Now, so usually in the tank, yeah, we will put a buffle. Yeah, a buffle. Yeah, if you see here, the buffle is this two plane placed vertically. Yeah. Yeah. Okay. Yeah. Now the baffle is needed to reduce the swirling and vortex. Yeah, while promoting a better mixing. Yeah, so as you can see, yeah, we have plates hung vertically here. Yeah, on the sides of the tank. Yeah, this we call baffle. Yeah, so it's actually a vertical plate with a diameter of 1/12, yeah, of the vessel diameter installed perpendicularly on the tank wall. Yeah. Okay, so this vertical plate is installed perpendicularly on the tank wall. Yeah. And the diameter, yeah, I mean the width of the vertical plate here, this one. Yeah. The width of the vertical plate, yeah, is only 1/12 of the total vessel diameter. Yeah. So if this width compared to the diameter is 1/12. Okay, now, okay, and then the baffle is usually placed with a little gap in between the tank wall and baffle. So it's not directly installed exactly on the tank wall, yeah? Usually there would be a little gap in between the tank wall and baffle, and then they only weld on the top and yeah, on the bottom. Yeah, just like a small, they use like a small, maybe like a pipe, yeah, steel pipe, yeah, and weld the tank wall and the baffle, yeah, right on the top and on the bottom. Yeah, but in the middle, yeah, there will be a little gap in between. Okay. Okay, now, yeah, to promote a good mixing with no vortex, usually in one tank, we install 4 baffles. Yeah. Yeah, you may see figure 3.43. Figure 3.43. Let me see. Okay, this one. Yeah. Yeah, for the buffer tank. So if you see here, the vertical, small vertical lines here, 2 small horizontal lines here. Yeah, this actually the buffer. Yeah. Okay. If you see from the side view, yeah, this are these are the buffers. Yeah, this. As you can see, there is a small gap in between the buffle and the tank wall, and they use only like, I think like a small pipe, yeah, a small steel pipe, yeah, to connect the tank wall with the buffle. Yeah, so they weld the last, yeah, they weld the the steel pipe, yeah, to the baffle on one end, and the other end is to the tank wall. Okay, now, okay, yeah, I have 4 videos, yeah, to show you the unbuffled tank and the buffled tank, and you can see the difference between the two. Yeah, for unbuffled tank, they will usually form vortex, and it will reduce the mass transfer. While for buffled tank, yeah, it will give you a good mixing, yeah, with no vortex. Okay. Uh, okay, again, you can see, yeah, you can watch the 4 videos. Yeah, you can just pause this video. Yeah, and then switch it to the 4 videos. Yeah, after you finish with the 4 videos and you know what the differences are between the buffered tank and unbuffered tank, then you can continue this class. Yeah, and continue to watch this video. Okay, yeah. Okay, so there are several types of agitator. The first one is three-blade propeller agitator. Okay, so I will go up again to this uh to this figure. Yeah, as you can see, yeah, it's just like a fan. Yeah, yeah, the three-blade propeller agitator, the shape looks like a fan. Yeah, yeah, it can be center mounted or side entering. Yeah, let me annotate. Wait, okay. So it can be put like this. Yeah, it's center mounted. Sorry if I draw it not really center at the center. Yeah, or it can be side entering like this. Oh, sorry. Let me undo. Yeah. So it can be placed in the center mounted, or it can be placed from the side. Okay, let me go. Yeah. Oh, wait, they're all drawing. Okay, now, and then, yeah, the rotational speed for this type of agitator is from 400 to 1750 RPM. Yeah, and it's usually used for low viscosity liquid. Yeah, less than 3000 CP. And then the type of flow, yeah, it's axial pattern. Yeah, axial pattern. Yeah, why? Because it's due to the direction of the tilted blade. Yeah. So maybe okay, yeah. So maybe I can go first to the figure 3.4-2 in your Genco, please, yeah? Okay, so this is the top view of these four agitators. Yeah. Okay, if you can see here, yeah, the blade of the, if you can see from the top side of the agitator, yeah, you can see that these three A to C agitators, yeah, the blade is perfectly vertical. Yeah, it's placed perfectly vertical. Yeah, it's not tilted. Yeah, now usually this type of agitator, yeah, the first three agitator, yeah, usually will cause a radial flow. Yeah, will cause a radial flow. Yeah, because the blade of the agitator is placed perfectly vertical, in a perfectly vertical manner. Yeah, while for this D, yeah, so for this agitator, as you can see, the blade is tilted. Yeah, the blade is tilted. Yeah, so it will cause an axial flow. Yeah. If you see here, yeah, if you see from the figure on the right, the three-blade propeller agitator, yeah, you see the blade is a little bit tilted. Yeah, it's not perfectly vertical. Yeah, so it will form the axial pattern of the flow. Yeah, okay. Now, okay, and then the second one is paddle agitator. Yeah, so it's actually similar to these two. Yeah, 3.4-2 A and B. Yeah, it's paddle agitator. Okay, yeah. 2 and 4 pedals are the most common type. If you see here, it's only 2 pedals. Yeah, however, if they have another pedal, yeah, perpendicular to the first pedal, then we call it a 4 pedal agitator. Okay, yeah, so 2 and 4 pedals are the most common type. Yeah, the rotational speed is usually from 20 to 200 RPM, and it's usually used for a very viscous liquid, yeah, from 50,000 to 500,000 centipoise. Yeah, so it's much higher than the left agitator. Yeah, it's only 3,000. It's start from 50,000. Okay, the type of flow is radial because the direction of the pedal is perfectly vertical. Yeah, and then the total length of impeller. Yeah, the ratio of total length of impeller to the diameter of the impeller. Yeah, is actually 60 to 80% of diameter of vessel or tank. Yeah. Okay. So if I want to know, if I know the diameter of the vessel, yeah, it's 1 meter. Yeah, so the diameter of the impeller or the total length of impeller. So it's not the ratio, sorry, yeah. It's not the ratio. So the total length of impeller, yeah, the total length of the impeller is actually the same as the diameter of the impeller. Yeah. So some books use length of impeller, some will use the diameter of the impeller. Yeah. So the total length of impeller or the diameter of impeller or dA, yeah, is actually only 60 centi to 80 centimeters. Yeah. If the diameter of the vessel or tank is 1 meter. Okay. Yeah, I will repeat again. Yeah. Yeah, it's not ratio, sorry. Yeah, so the total length of impeller, this part, or sometimes, yeah, we call it as a diameter of impeller. It's also this one, yeah, or dA. Yeah, it's actually only 60 to 80% of the diameter of the tank. Yeah, so if I have 1 meter diameter of tank, that means the dA value is only 60 centimeters to 80 centimeters. Now, the width of the blade, so the width of the blade is this. Yeah, the width of the blade is this side. Yeah, is 1/6 to 1/8 of dA. Yeah, so let's say if the dA is 60 centimeters, then the width of the blade is only 10 to 1/8 over 60. Yeah, 1/8 multiplied by 60. 7. Yeah. 10 centimeters or less. Yeah, I think like 7, 8, something like 8 centimeters to 10 centimeters. Yeah, the width of the blade. Okay. Now, at a higher speed and no baffle tank, yeah, the liquid is just swirled around without no actual mixing. Yeah, with a higher speed and no baffle tank, the liquid is just swirled around with no actual mixing. Yeah, because yeah, the type of the flow is in radial pattern. Yeah. So the liquids on the bottom side will stay in the bottom side. Yeah, the liquid on the top part of the tank will also stay still in the top part of the tank. Yeah, at a higher speed and no baffle tank. Yeah. So there is no actual mixing. Okay, because the type of the flow is in radial pattern and they have no baffle. If they have baffle, usually it will promote a good mixing because of the impact between the liquid with the baffle. Okay. Nah. And then we also know we have the turbine agitator. Yeah, so it's this two. C and D 3.4-2C and C.4-2D. Okay. Yeah. It actually resembles the multiple paddle agitator, however, it has shorter blades. Yeah. It's similar to the paddle agitator, however, with shorter blades. And it can be used at a speed at a high speed and also viscosity of less than 100,000 cp. Yeah. Nah, the total length or the diameter of the turbine, yeah. So the total length, so from this end to that end, yeah, the total length or the diameter of the turbine of dA, or we call it dA, is actually 30 to 50% of dP. Yeah, so if I have the tank diameter of 1 meter, that means the diameter of the turbine is only 30 centimeters up until 50 centimeters. Yeah, so from this end to this end. Okay, now usually have 4 to 6 blades. Yeah, now turbine with flat vertical blades is good for radial flow. Yeah, so it's good for dispersing gas. However, we also have the pitch blade. Pitch blade is just like this. This is the turbine with flat vertical blades. It's like this. Yeah, so it's perfectly vertical. Yeah, the plate is placed perfectly vertical. Yeah, for this one is the pitch blade. Yeah, so the blade is placed a little bit tilted. Yeah, so it's good for the radial axial flow. Yeah, suitable for the suspension of solids. Yeah. Okay. Nah, and then we have another agitator. Yeah, we call it helical ribbon and helical screw agitator. Yeah. Now, this is used for a highly viscous solution. So if you are in the plant of, let's say, sari roti, yeah, you know sari roti, right? When you want to mix the dough, yeah, they will not use a common mixer, yeah, like the one we use at home, yeah. They will use this kind of mixer, yeah, because they have to mix the dough, yeah, and it's very viscous, right? Yeah. Now, so this type of agitator helical ribbon or helical screw, yeah, is used for a highly viscous solution, yeah, from 1,000 to 25,000 Pascal second. Yeah, and usually it operates at low RPM in the laminar region. Yeah, and ribbon and screw are formed in a helical path and attached to a central shaft. So if you see there is a shaft here, and then the ribbon or screw, yeah, is attached, yeah, on the central shaft. Yeah. Now, the type of flow is a combination of axial and radial. Yeah, where the fluid moves in the turtle's path down the center and up along the twisting motion. Yeah, yeah, because of the shape of this agitator. Okay, and then how do I select the agitator? Yeah, so it actually mainly depends on the liquid viscosity. If we want to make the paste, yeah, to mix the paste or to mix the dough, then usually we will just use this type of agitator. However, if it's only like let's say sugar solution, then maybe a 3-blade propeller is enough. Yeah, or the paddle is enough. Yeah, so it depends on the liquid viscosity. Yeah. Now, if the viscosity is higher than 2.5 to 5 PAS, yeah, generally I can say that buffers are not needed. Yeah, because if they have this value of viscosity, usually it's already very viscous. Yeah, since it's very viscous, yeah, usually the mixing will cause only a little swirling. Yeah, only little swirling is present. So that's why buffers are not needed for liquid with viscosity higher than this one. Yeah, greater than these values. Okay. Now, in the industries, yeah, in common industries, yeah, not only sari roti, yeah. Common industry, usually we use turbine agitators. Yeah, turbine agitators. Nah, wait, where is it? Oh, wait a minute, yeah. Let me see. Where is the table? Oh, let me find the table first. Ah, this one, yeah. This one, yeah. Now, the geometric proportion for a standard agitation system, yeah, can be seen in table 3.4-1. Yeah, now see figure 3.4-3C for nomenclature of the symbol. Yeah, so figure 3.4-3. Let me see, where is it? Ah, this one, yeah. I will make it a little bit bigger. Okay, yeah. So dt is the diameter of the tank. dA is the diameter of the blade, yeah. Diameter of the agitator. Yeah. Okay. And then L is the length of the blade for each blade. Okay. And then C, yeah, is the space from the bottom of the tank to the bottom of the agitator. Yeah. H is the liquid height. W is the width of the agitator. Okay. Yeah. J is the width of the baffle. The width of the baffle. Yeah. DD, yeah, is the diameter of the agitator up until the center line of the blade. Yeah. Okay, so yeah, when you see table 3.4-1, yeah, you have to also see this figure so that you know the nomenclature. Yeah, okay, so I will go back down, yeah, to the table here. Yeah. Now, so the geometric proportion for a standard agitation system, yeah, usually the dA over dt, yeah, the diameter of the ratio of diameter of the agitator to the diameter of the tank is 30 to 50%. Now, the height of the liquid to the ratio of the height of the liquid to the diameter of the tank is usually regarded as 1. Yeah. This is standard agitation system, yeah. Yeah, the ideal one. Yeah. It can change, yeah, later according to the problem. Okay, but this is the standard agitation system. Okay. C over dt, yeah. I will go up. What is C? I forget. Oh, C. C is the space between the bottom of the tank to the bottom of the agitator. Okay, so the distance between the bottom of the tank to the bottom of the agitator over dt, the diameter of the tank, is 1/3. Yeah, and so on. Okay. Nah, nah, yeah. So this is the typical standard design of agitator. However, there are several additional informations. Yeah. So in some cases, yeah, the width of the blade over the diameter of the blade is not 1:5, but 1:8. Yeah, as in figure 3.4-5, curve 2 and 3. So if we go down, this or the 8, Wait a minute. Why can I see? Oh yeah, that one. Yeah, this one. Yeah, as in curve 2 and 3. Yeah. So as in curve 2 and 3. Yeah, curve 2 and curve 3. Yeah, you can see the a note here. So curve 2. Yeah, the ratio between the dA to W is 8, or I can say W to dA is 1/8. Yeah. Yeah, so for a flat 6-blade open turbine, yeah, the W/dA is 1/8. Yeah, in some cases, just like the curve 2 and also curve 3, 6-blade open turbine, pitch blade, but blade at 45 degree. Yeah, it's also W/dA-nya 1/8. Yeah. Yeah, so that's why I said, yeah, even though we have the standard geometric proportion here, this is actually for the ideal agitation system. Yeah. But as I said, there's nothing ideal, yeah, in the world. Okay. So it may change. Yeah. So in some cases, it's not 1/5, but 1/8. Okay? And also in some cases, yeah, the ratio of baffle width J, yeah, to the tank diameter dt, yeah, is 1/10. Yeah, here is 1/12, right? In the table 3.4, that's one. Yeah. But here in curve 4 and 5, yeah, if I scroll it down again, curve 4 and curve 5, yeah, I will see the note here, curve 4. Yeah, the dt over j is 10, or I can say j over dt is 1/10. Yeah. And curve 5, yeah, for propeller, yeah, j per dt is also 1. Okay, so you have to pay attention, yeah, to the problems, yeah. Pay attention to the problems, yeah, because not will follow the table 3.4-1, but some will follow the curve, yeah. So this is an important note, that's why I put it in red, yeah. If you don't know anything, no clue, no known typical ratio provided anywhere in the problem, so use the standard design proportion. Use this table 3.4-1. However, if there is a clue or there is a known typical ratio provided in the problem, then you have to follow that. Okay. Now, the number of baffle is 4 in most systems. Now, the clearance or the gap between the baffle and the tank wall. Yeah. Yeah. So a little gap in between the tank wall and baffle is 0.1 to 0.15 times J. Yeah. J stands for baffle width. Okay. Now, why do we keep this gap actually? Yeah. So this gap is to ensure the liquid does not form a stagnant pocket next to baffle and wall. Yeah. Okay. Because if there is no clearance, if there is no gap at all between the tank wall and the baffle, then maybe some of the liquid will stay in the corner, yeah, and form a stagnant pocket. Yeah. So it will not give you a good mixing. Yeah, because there's still a liquid retained in the corner between the baffle and tank wall. Yeah, that's why we have to add the gap, even though it's little. Yeah, yeah, to ensure there is no stagnant pocket and the mixing can be conducted perfectly. Yeah. Okay. Now the next topic is how do we calculate the power? Yeah, in the agitated vessel. Yeah. Oh, sorry. Now, The power in agitated vessel cannot be determined theoretically, yeah, but can be approached using an empirical correlation, yeah, using the impeller Reynolds number. Yeah, so we know another Reynolds number, yeah. We have already know the common Reynolds number, the Reynolds number of fluidized bed, NREF, or NREP, yeah, a Reynolds number of the packed bed, yeah. And now we know the Reynolds number for the impeller or NRE accent. Yeah. Okay, so how do we calculate the Reynolds number for impeller? Yeah. We will use equation 3.4-1. Okay, so here. Yeah, equals to dA square. Yeah, diameter of the agitator square times N. N is the rotational speed. Yeah, usually it's not in RPM but in RPS. Yeah, so if in the question it's known in RPM, then you have to convert it to RPS times the density of the liquid over the viscosity of the liquid. Yeah, nah, the range of the NRE accent, yeah, laminar is when the NRE is less than, NRE accent is less than 10. Turbulent is when the NRE accent is higher than 10,000. In between is transitional. Yeah, so it's again a different number compared to the fluidized bed NRE, packed bed NRE, also the common NRE. So it's different value again. Yeah, this you have to pay attention to this. Okay. Now, the NRE accent, yeah, the value of this NRE accent can be correlated to the power number. Yeah, the power number of the agitator. Okay. Power number is NP. This NP, yeah, can be used to obtain the power. Yeah, so we can go to equation 2 and 5. Yeah. Okay, so by knowing the NRE accent, we can know the NP. Once we know the NP, then we can know the P. Yeah. Oh, it's equation 2 and figure 5. Sorry, it's not equation 5. Figure 5. Yeah. So, yeah, how to find the NP then? Yeah, from the NRE. Okay, so from the NRE, yeah, we know a value, right? Let's say 100. So 100 is here. Okay. And then we draw a vertical line until it passes through the curve that we want. How do we know the curve that we want? Yeah, you have to see the requirement. Okay, so if I use a flat 6-blade turbine with disc, yeah, with this geometry, yeah, with this geometry, so all requirement are met. So I will use curve 1. Okay, so I will draw a vertical line, yeah, from the NRE of 100 to curve 1, yeah, until it passes through the curve 1, then we know there is a meeting point here, right? There's a meeting point here, then I draw a horizontal line, yeah, until it crosses the x-axis, the y-axis. Then we know the value of, once we know the value of NP, then we can just multiply it with the density, and then n to the power of 3 and the a to the power of 5, then we can know the power value. Yeah. Oh, miss, I don't use the flat 6-blade turbine with this. I use the flat 6-blade turbine, yeah, with this geometry, yeah, dt over j12, dA over w8. Okay, so you use the curve too, yeah. So it's only, yeah, so when you drag down, when you draw a vertical line, it's only up until this, yeah, and this is the meeting point. Again, draw horizontally, yeah, draw a horizontal line up until it crosses the y-axis, then you know that, okay? Yeah. Okay, so how you choose curve 1 to 6, yeah, depends on the problem. Yeah, depends on what kind of impeller you use. Yeah. Okay. Okay, now the figure of 3.4-5, yeah, is actually used to mix the Newtonian liquid contained in a baffled and cylindrical vessel. So if the vessel shape is not cylindrical but cubes, yeah, then we cannot use this figure. Yeah. And it's designed for a baffled tank. However, can I use it for non-baffled tank? Yes, you can use it for non-baffled tank. However, yeah, it's only applicable if your NRE accent is less than 300. Once it goes over 300, then you cannot use figure 3.4-5. Okay. Yeah. Okay. Yeah. When the NRE accent is higher than 300, yeah, the power consumption for unbuffled vessel is generally less compared to the buffled one. Yeah, but we cannot calculate, yeah, because this figure is applicable only when the NRE accent is less than 300. Yeah, for unbuffled tank. Okay. Okay, we go to example 3.4-1. Let me drink first, okay? We have a flat blade turbine agitator with this, having 6 blades installed in a tank similar to the figure of 3. The dt is 1.83, the dA is 0.61, the dt equal to the height of the liquid, the width of the blade is 0.122, the tank contains 4 baffles, so it's not unbaffled tank. So we can use figure 5. It's having a width J of 1.15 meter. The turbine is operated at 90 RPM. We have to make it to RPS, convert it to RPS. And then the liquid in the tank has viscosity of 10 centipoise. The density is this, 929 kilogram per cubic meter. Okay, the first question, calculate the required kilowatt of the mixer. The second one, for the same condition, sorry for the disturbance. The second one, for the same condition, except for the solution having a higher viscosity. So it's not 10 CP again, but 100,000 CP. We are asked to calculate the required power. Okay, so for part A, yeah. Now the following data, yeah, the dA 0.16, 0.61, W 0.122, dt 1.83, J is 0.15, N is 1.5 RPS, density is this, the CP, the viscosity is this. Yeah, we convert it all to SI number, SI units. Then we can calculate the Reynolds number. Yeah. Okay, so this, yeah, 51,850. Okay, and then using curve 1, I want to use curve 1. Why? Because it's flat blade turbine agitator with disc. Yeah. Okay, I can scroll it up. Flat turbine with this 6 blade. I will see. 6 blades. Yeah. Okay, yeah, so it's curve 1. However, I have to make sure that these requirements are met. These two requirements are met. Yeah, I have to make sure first. If it's not, if one of them are not met, then I cannot use this figure. I cannot use this curve. I have to find another one. Okay, 4 baffles, dA over W5, dT over J12. 4 baffle contains 4 baffles. Okay, that's good. Yeah, so it's baffled tank. And then I have to make sure, yeah, dA over W should be 5 if I want to use curve 1. dT over J should be 12. Okay, now then I have to, yeah, I have to divide this dA over W. Yeah, 0.61 over 0.122. It's 5. Oh, it's math. And then dt over j, 1.83 over 0.15. Oh, it's 12. Yeah. So I can use curve 1. Okay. Now, yeah, it turns out that the NP is 5. Yeah, the NP is 5 for NRE of this. Yeah, then I can solve the P, yeah, using equations 2. Yeah, so I put 5 here. The density is this, right? And then n is 1.5 to the power of 3. dA is 0.61 to the power of 5. Okay. So the power for agitator is 1.77 horsepower. Okay, so for part B, yeah, the viscosity is not 10 centipoise anymore. Yeah, but 100 centipoise, so it's 100 kilogram per meter second. So I put it here. NRE, Xn is 5.185. This is in laminar region, yeah, because it's less than 10. Okay, so again, I use the same curve, curve 1. Yeah, because it's flat blade with turbine, with this, flat blade turbine with this. I have 6 blade. The dA over W is 5. The dt over J is 12. Yeah, all requirements are met, so I can use curve 1. Then from figure 5, I can find the NP is 14. Yeah, so again, I put all the known numbers here, then I can know that the power is 5 horsepower. So as you can see here, the higher the viscosity of the liquid or the fluid, yeah, the higher the power required. Okay. Okay. Yeah. Okay, and then the variations of various geometric ratio, yeah, from the standard turbine design will also have an effect on NP in the turbulent region. Yeah. So variations of various geometric ratio, yeah, from the standard design, yeah, may have an effect on the power number in the turbulent region. Yeah. First, for 6-blade open turbine, yeah, the NP is actually equal to the W over dA to the power of 1. Yeah. And then for 6-blade open turbine with dA over dt varies from 0.25 to 0.5, it has no effect on NP. Yeah. Now, and if we have an agitation system with 2 blades, yeah, previously from the figure, from the table, we have only one turbine, right? One propeller, yeah. Now, if I have 2 turbine or 2 propeller like this, yeah, Now, installed in the vertical distance between the two turbines equals to dA. Yeah, so dA here equals to the vertical distance of the two turbines. Then the total power of the particular system is actually 1.9 times the single six-blade open turbine. Yeah, this the problem say that there are two turbines, there are two propeller. Yeah, so use the calculation method of the single turbine first. Yeah, and then after that multiply it by 1.9 times. Then you can get the total power of this system, of this two turbine system. Yeah. However, the requirement must be met. Yeah, the dA must be the same as the vertical distance of the two turbines. If the vertical distance of the two turbines is not the same with the dA, then we cannot use this empirical approach. Yeah, we cannot do it. Nah. Okay, and then if we have an agitation system, again, with two pitch 45-degree blade turbines installed with vertical distance of the two turbines equal to A, then the total power of this system is again 1.9 times higher than the single pitch 45-degree blade turbines. Okay. Okay, nah. Okay, nah. A baffled and vertical square tank. A baffled and vertical square tank. Yeah. So if I have a tank, yeah, cubic tank, yeah, and I have baffled installed inside the tank, or a horizontal cylindrical tank, yeah. These two has the same NP number as the vertical cylindrical tank. Yeah, the change is only in the flow pattern occurs. Yeah, okay. So if I have a baffled and vertical square tank, or if I have a horizontal cylindrical tank, yeah, I can say that the NP, or the power number, yeah, is the same as the vertical cylindrical tank. Yeah. Yeah, the change is only in the flow pattern occur. Nah. Nah, Miss, how about if I use another impeller not mentioned in figure 5? Yeah. Let's say, yeah, a pedal agitator. Yeah, if you see from figure 5, I will scroll it up. Yeah. Curve 1, flat 6-blade turbine. Curve 2, flat 6-blade open turbine. Curve 3, 6-blade open turbine. Curve 4, propeller. Curve 5, propeller pitch. Curve 6, high efficiency impeller. No pedal impeller. Yeah? No pedal impeller. So how should how can I calculate the power then? Yeah. Now, for the anchor type, yeah, this anchor, yeah, kayak jangkar kan, kayak anchor, yeah. Yeah. The NP for anchor type, yeah, for pedal anchor type. Yeah. Nah, for NRE action less than 100, yeah, you can use equation 3 with typical ratio dA over dt 0.9, W over dt 0.1, C over dt 0.05. Yeah. Okay, so I will go down. Yeah. Okay. Yeah. Okay. Yeah. So yeah, when you use the anchor type, yeah, when you use the pedal anchor type like this, yeah, then you can use equation, then you can find the NRE action first. Yeah. You can find the NRE action first. And after that, put the value of NREXN here in the equation 3. Okay. And you can find the NP. Yeah. But make sure that the NREXN that you put here is less than 100. If it's higher than 100, means, can I use this equation? No, you cannot. Yeah. Yeah. But if your NREXN is less than 100, then you can use this equation 3. Yeah. But you have to make sure as well, yeah, the typical ratios are met. Yeah, if the typical ratios are not met, you cannot also use this equation. Yeah. Okay. So the NREXN must be less than 100. The typical ratios must be met. Then you can use equation 3. Once you can find the NP number, then you can find the P. Yeah, using equation 2. Yeah, P times density times n to the power of 3 times the a to the power of 5. Yeah. And then, if I have an agitator with helical ribbon shape, yeah, nah, what kind of equation should I use? Yeah, you can use equation 4 and equation 5. Yeah, okay. Now, but this specification must be met. Yeah, the NRE action must be less than 20. Yeah, the NRE action must be less than 20. Then you can use these two equations. Yeah, and then the dA per dt, W per dt, yeah, must be in this range. Yeah. If one of these, yeah, if you cannot fulfill, yeah, this requirement, then you cannot use these two equations. Okay. Then again, after you find the NP number, yeah, then you can use equation 2 to find B. Okay. So, Miss, in equation 4, there is a note here. Agitator pitch per tank diameter equals to 1. For this, agitator pitch per tank diameter equal to 0.4. But how can I measure these two? Yeah, okay, nah. Yeah. Yeah, in the agitation system, yeah, we will know one term called agitator pitch. Yeah, which is the vertical distance of a single flight of the helix in 360-degree rotation. So for helical ribbon or helical agitator, yeah, the blade will, form a helix, yeah, memutar, yeah, in a 300-degree rotation, ya, memutar 360 derajat, ya. Oke, nah, the height, ya, the height or the vertical distance of a single flight of the helix in a 360-degree rotation, yeah, we call it as an agitator pitch. Okay, nah, if the agitator pitch divided by the dt equals to 1, then you have to use equation 4. However, if the agitator pitch divided by the tank diameter and it equals to 0.5, then you have to use the equation 5. Yeah. So, yeah, in this subchapter, yeah, of agitation, yeah, in the subchapter of this agitation system, you have to be very careful with all the requirements. Yeah. So, yeah, if in the problem the agitator pitch to tank diameter ratio is 0.5, you cannot use equation 4, even though it's also for the helical ribbon. Yeah, but this requirement yeah, you cannot fulfill, right? Yeah, so you cannot use equation 4. Yeah, and vice versa. You cannot use equation 5 if the agitator pitch through tank diameter is equal to 1. Yeah, you cannot use equation 5. Okay, so you have to be very careful, pay attention to all the requirements for each equation. Okay. Nah. Okay. Nah, if you have any question, yeah, you can just ask directly in the class, yeah, or you can just drop me a message on my WhatsApp, or you can just directly drop a message or comment in this YouTube video. Okay. Nah. Okay. Now I will go to the agitator scale up or scale down, perbesaran atau pengecilan. Yeah. So scale up and scale down are needed to adjust the capacity according to the industry capacity. Okay, now the procedure is as follows. Yeah, so first we have to calculate the R. R is the ratio of scale up or scale down. Yeah, now in the subchapter, yeah, we assume that the diameter of the vessel dt equals to the vessel height or h, yeah, or the liquid height. Yeah, now we can use this equation of 6 to 8. Yeah, 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 to find the R. Yeah, to find the R. Yeah. So equation 6, yeah, can be derived to equation 7. Equation 7 can be derived to equation 8. Yeah. Note that R is a scale up or down ratio. Yeah. Or volume ratio to the power of 1/3. Volume ratio to the power of 1/3. Yeah, I emphasize this, yeah, because it's very important. Volume ratio of to the power of 1/3. Yeah, it is actually equivalent with tank diameter ratio only if the tank diameter equals to the height of the tank. Yeah, if dt equals to h, then the volume ratio to the power of 1/3 is actually the same as the tank diameter ratio. Yeah. Nah. However, if the tank diameter is not equal to the height of the tank, then we cannot use the volume ratio to the power of 1/3 equal to the tank diameter ratio. Cannot. Yeah. It must not be equal. Yeah. Nah, another case, yeah. Oh, this from the problem, I don't know whether the dimension of the tank is the same as the height of the tank. Yeah, it's not specified anywhere. Then you can assume that dt equals to h. However, if in the problem they mention that the tank diameter does not equal, yeah, to the height of the tank, then I cannot use, yeah, the principle of volume ratio to the power of 1/3 equals to the tank diameter ratio. Cannot. Yeah, it's very important. Okay. And then after you found the value of R, yeah, then change all the dimension value of agitated tank. Yeah, with examples shown in equation 9. Yeah, so dA after scale up or scale down must be the same as R times dA before scale up or scale down. J2, yeah, J after scale up or scale down equals to ratio of scale up or scale down times the J before scale up or scale down. dt2 equals to R dt1 and so on. Okay. And then the agitator speed of scale up or scale down, yeah, may follow the equation 10. Yeah. Okay. So the agitator speed of the scale up or scale down will follow this equation. Yeah. So equation 9 applicable for the dimension value of the agitated time, while for the rotational speed of the scale up or scale down, the rotational speed after it's being scaled out or scaled down can be calculated using equation 10. So it's not n2 equals to r times n1, yeah, but n2 equals to n1 times 1 over r to the power of n. Yeah. Okay. Now, what is the value of n here? Yeah, the small n here. Yeah. So the value of n here differs in different condition. Yeah. So for equal liquid motion, the n value is 1. Yeah. For equal suspension of solids, the n is 3/4. 3/4, sorry, 3/4. Yeah. And then for equal rate of mass transfer, or sometimes we call it an equal power per unit volume, then the n value is 2/3. Yeah, now this value of n is actually based on empirical and theoretical consideration. Yeah. So if you ask me, Miss, where do you get this value? I don't know. Yeah, it's based from the empirical, so from many research, yeah, many experiments, and then they can find this value. Okay, so if I have a process, yeah, that I want to scale up, yeah, with an equal liquid motion, then actually I can use n equal to 1 for this case. However, if in the problem they said, I want to scale it up, but with equal mass transfer rate, then I can use this 2/3 as n, yeah. This 2/3 value, yeah, to be input here. Now, by knowing the new agitator diameter and then the new rotational speed after scale up or scale down, then the power required can be calculated using figure 5 and equation 2. Okay, so now we read the example 2 and 3, but before that, I want to give you some note here. Yeah, so the first note is the tip speed. Yeah, so later in example 2, you will find new term called tip speed. Yeah, so tip speed can be expressed as a pi times dt times n. Yeah, because pi times dt equals to perimeter of the tank, m per revolution. Yeah, and n is equal to the rotational speed or revolution over second. So when I multiply these two terms, becomes pi times dt times n, it has a unit of meter per second. So I can say that tip speed is actually the velocity of the tip or velocity of the blade rotating, yeah, the vessel. Okay. Now, for the second one, I will give, for the second note, I will give it after we discuss the example 2 and example 2. So we go to example 2 first. Yeah. For the scale up rule exponent in equation 10, show the following for turbulent agitation. Yeah. So we have to prove, yeah, when we have the equal power per unit volume, yeah, will n equals to 2/3. Yeah, so if we have an equal power per unit volume, yeah, will the n equal to 2/3? Yeah, we have to prove it. And then the second question, if we have the n equal to 1, will the tip speed constant? Yeah, so we have to prove. Yeah. Okay, so for the first one. Yeah. Yeah, for the first one, yeah, we know that NP can be obtained using the figure 5, right? And then after that, the power can be obtained using equation 2. Yeah. So for power before the scale up or scale down, yeah, we can use this equation. After scale down, we can just change the subscript here to 2. Yeah, after the scale up. Then we can get P1 and P2. Okay, then we have to prove whether if we used an equal power per unit volume, the N will be equal to 2/3. Now, we will use this condition, yeah? P1 over V1 equals to P2 over V2, yeah? Yeah, so for equal power per unit volume, then this requirement must be met, right? So P1 over V1, yeah, it's P1 over pi times dt1 to the power of 3 over 4 equals to P2 over V2. It means P2 equals to pi times dt 2 to the power of 3 over 4. Yeah. Yeah, so we have to prove whether this requirement will result in n equals to 2/3. Yeah. Okay, so we substitute this equation to here and substitute the corresponding P2 to here. Okay. Combining these two equations, then we can get this. Yeah. Okay. And it turns out that the n, yeah, here is equal to 2/3. Okay, so it's proven. Yeah, for A, it's proven. Okay, so for B, yeah, when the n equal to 1, will the tip speed constant? Yeah, so we will use the equation of 10. Yeah, we will use the equation of 10. Yeah, and then multiplying by pi, and then we can get this. Yeah, and then yeah, by sorry, wait, let me see. Let me go up. Oh yeah, sorry. Yeah, by multiplying by pi, then we can get this equation. Yeah. Okay. Yeah. So for n equals to 1, and I put 1 here. So n2 times dt2 equals to n1 times dt1. Right? And then multiply it by pi on the left-hand side, pi on the right-hand side. Then I can get this. So pi times dt2 times n2 equals to pi times dt1 times n1. This is tip speed before scale up. This is tip speed after scale up. Yeah. So I can say that the tip speed is constant. Yeah, if I use n equals to 1. Okay. So it's proven again. Yeah. Okay. Yeah. Some approximate guidelines for determining the power to volume ratio for fluid with normal viscosities. Yeah. Yeah, it's actually 0.1 to 0.2 kilowatt per cubic meter for mild agitation and blending. Yeah. 0.4 to 0.6 kilowatt per cubic meter for vigorous agitation. Yeah. 0.8 to 2 kilowatt per cubic meter for intense agitation or when mass transfer are important. Okay. Yeah. So these are the notes. Yeah. Now, for the first assignment, yeah, you have to derive equation 12 to equation 13. Yeah, you have to derive equation 12 to equation 13. Yeah, using the equations given in subchapter 3.4. So how can I get this equation 13? Yeah, by using this equation. Okay, so you have to derive. Yeah, you have to do derivation. Okay.